1, booster ignition, and liftoff of the Space Shuttle Discovery, returning to the space station, paving the way.
Hello and welcome to Across the Kármán Line, a KCL Space podcast where we talk all things space. Today is our first ever in-person podcast, and I have a very special guest with me, somebody I've known for 3 years at university, Louis. Louis is an undergrad in math from Sorbonne in France in 2013, followed by a PhD in 2017 from Brown. Followed by a master's from Brown, and then is currently a PhD student at King's from 2019 onwards, where he's specializing in dark matter phenomenology and is doing a minor in black hole physics, studying the information paradox. So over to you, Louis. How are you?
Hey, I'm good. Yeah, thanks for having me on this thing.
Right. So before we get into the topic for today, just a little bit about what your research is. How have you been involved with physics at King's and other stuff?
Sure. So, like you said, I arrived in 2019, and I'm kind of involved in so my advisor is Chris McCabe, and so that means that I naturally gravitate a bit towards dark matter phenomenology, but that can still be very wide-ranging. So you can have experiments on Earth, you can have model building in particle physics, you can have looking at astro or astrophysics data. You can have also, there can be, you can look for modifications to standard cosmology or even to black hole physics if you're looking for signs of quantum gravity. There's all sorts of things you can look for basically that are extensions of the standard models
Right.
that we have for the world around us. And I'm a weirdo in the sense that I don't really conform to a single topic. Typically, I think a lot of people in their PhD, they end up doing just one thing and they get really, really specialized at it. And I have been forced to do that at first, but then have, as soon as I could, started to work on other topics as well. Yeah.
Well, the topic we're discussing today is nowhere close to what you're doing a PhD in.
Yeah, it's true. It's pretty different. Yeah.
So, that's good though. Just good flow of knowledge.
Yeah, but it's still something I was kind of obsessed with, I guess, recently because it was in the news so much,
right? And
it was all over my feed, on social media. I guess I have a very nerdy feed, basically.
Well, you're doing a PhD in physics.
Yeah.
Right. So let's get into the topic. So we're discussing the James Webb Space Telescope today. Let's just get into it straight up because it started going into the direction of moving away from Hubble. Moving away from Hubble into the next step in astronomy around the time when you had your first interest in curiosity, when you were probably a very small kid, right?
Yeah, probably. I think I started getting interested in it just around the year just before 2000. Okay. So I think Hubble has been up there since 95.
Yes.
So I guess they were developing already James Webb. I think, if I'm not mistaken, I think I saw this on Wikipedia, it was that it was meant to come out in 2004 or 5 or something like that, James Webb. And as you can see, 17 years later, we just barely got it up there.
Right. So before we get into the engineering aspect of things and then physics, why is that? What's the need of making another telescope if the Hubble's already been out there for so long?
Well, the Hubble telescope only sees so much and was made only given the technologies that were available at the time. So obviously it went up in 95, but it became operational, went live, but it was in development for maybe 10 plus years. And it was meant to be more, if I'm not mistaken, of a kind of galaxy cataloger. And it was there to fill a huge gap in knowledge of a certain kind of knowledge that was, actually, what is kind of the density of galaxies? What are the structures that galaxies form on a much larger scale? Things like this. And I think that at the time, there was really only there's only so much information. In fact, when it came up, we didn't even know, for example, about the acceleration of the universe, which came out in 99, and which was helped by, for example, things like the Hubble Telescope, because they could see They could look for supernovae in distant galaxies. They could look really far away. But it was still limited in the sense that so it's given us a lot of stuff. And if I'm not mistaken, I'm no expert about Hubble, but if I'm not mistaken, it's still running. It's still delivering some data.
Right.
And I think and so it's really I think it's remarkable what NASA's been able to do by where they were able to optimize what they could do with the Hubble telescope. But of course, once you've discovered a lot of things with Hubble, usually if science is doing its job, there'll still be a few little questions left over.
Yeah.
There'll still, or maybe you'll have discovered things, and those discoveries will raise new questions.
Yeah.
And I think that after a while, because you push your models to the extreme, right, until they break, and then you realize that kind of at that breaking point, the observations start to not really match.
Right.
And that's kind of what's happening already with the Hubble tension, which has nothing to do with the Hubble telescope.
Yeah.
Except maybe the fact that the Hubble telescope got the data for some of the Hubble tension, but it's more about the Hubble constant. And the problem is that to I think solve it, a lot of people are looking at trying to turn towards the earlier epochs of the universe. So pre-reionization, meaning before the first stars, and they're thinking, that the thought is that maybe we'll see more there, and that means that looking into that era, you need a whole new set of instruments, and of course engineering challenges, but yeah. Anyway, so that was probably a long-winded answer.
So the Hubble, like you said, is just a galaxy cataloger. So like Hubble essentially just clicks a picture in a way of whatever it sees, right?
Yeah.
So how exactly is the James Webb different from it?
Well, so James Webb is going to be taking data and pictures in a completely different spectrum of electromagnetic radiation. It's going to be doing it more in the infrared, and I think what they call, I forget. I think they call it near infrared and deep infrared, something like this. But the point is that that it's definitely outside of the visible spectrum. So what's nice with Hubble is that at least it actually gives us pictures that we can actually see, that we can make posters of. It's absolutely gorgeous. But this is going to be light that is kind of in a lower wavelength. A longer wavelength, lower frequency, and that kind of has a different purpose for cosmology. Yeah.
Right. It's also much bigger in size, which has been one of the major issues in manufacturing it as a whole. Because like something like that needs to be assembled in space, because like you can't transport an almost 6 meter big mirror up there, right? So like, what kind of challenges like do you think come in this kind of situation? Because clearly there was a lot of outrage in how much more expensive it is than its initial budget, how long it's been delayed, and all those issues. So why exactly does something like that come in like a self-assembly telescope in space?
Yeah, it was so expensive. Was it I think about 10,000% over budget?
Yeah. Just 10,000.
Yeah, just I just like that oh yes, these are our projections, and then this is what we have. Just orders of magnitude more expensive. But I think so I think the problems that came up were issues. There's so many issues that came up. Some of them were with the actual building of the telescope, and some of them were with all the way down to the materials, for example, to use, and how to actually make something that is going to have the right sensitivity, and that will be and have a long enough performance, and be light enough, etc. I think the difficulty with the price was mainly the engineering of it, and I think that the big one here, the thing that I think was the most impressive, was the solar shield, because you're trying to operate now something in the vicinity of a star, so next to the sun, but at about, I believe, 40 Kelvin, which is, or in Celsius about, was it minus 220 degrees Celsius? It's extremely cold, and that's in fact it's much cold. In fact, it's much colder than the vacuum of space itself at that point.
All right.
So they're trying to get really close to that near absolute zero, and for a giant telescope too. And there were, I think it was very complicated because there were so many steps, and that needed to function correctly, that at any moment, either one of them not working would have meant billions of dollars in waste, and as some people called it, it would lead to like the most expensive piece of space junk ever created, right?
Yeah. So why is it unfixable? Like, what's the issue in terms of why can't you, like, why is it like if it doesn't work, that's the end of it?
Well, I guess it depends on the actual thing that would break, obviously. But if, for example, if you say, so to give a bit of a picture of how the sun shield, for example, deploys, first, so this is after already a few steps that happened correctly, but that actually means that you need, for example, the sun shield is quite complicated. It actually is just a sheet that if you just held it in your hand, it would be completely malleable. It's just a very thin sheet of essentially aluminum foil.
Nice.
And it basically gets pulled apart. So these rods show up, these rods come out. If anything gets stuck in the rod, or a little thing was misplaced, or a screw that wasn't put in correctly, or anything like this, maybe you can't get that rod out, already catastrophe in the mission. Or for example, even in just the pulling out then, so then four little strings essentially would pull this this big sheet out. So basically like into a big kite shaped thing. And of course that has to work perfectly. If the tension in that, I don't know, it breaks off one of the sides or something like that, basically you're gonna make completely unreliable measurements, because the temperature, the radiation from the sun will be way too high. There's also the fact that it's not just one shield, it's actually, I think it's 4 or is it 5? I believe it's 4. Don't quote me on it, but where it's essentially creating insulation that way. And so once they've stretched out, they have to also then separate all 4 of them into the right separation for each of them. And so that of course multiplies by 4 the number of risky operations that you're doing. So it's really just like hundreds, actually no, it's hundreds just for the sun shield, but thousands of individual operations. And each of those, you have to essentially send a little code that a person is going to be given the order to compile. And that is going to send a radio signal out to it, and that is going to make its computer do that one little operation, and then it's going to say, it's going to tell you if it worked or not. And if you put anything wrong in that code, or your code is wrong in any way, then again, you could completely jeopardize the mission by doing one step too early, maybe, or too late. All you need is an indexing issue on in your library of thousands of little codes that you need to index. So it's no wonder that they probably wanted to practice and do everything 10 times before, to make absolutely sure it'd be perfect.
Yeah, I think more recently as well, like I agree, like I think the solar shield has been one of the most important things, right? Because placing something that close in the vicinity of a star, like I'm assuming a lot of infrared radiation just leaks in as noise in the data. And I think recently, before the launch, it ripped as well. So they had to, like, I think that was the most recent delay.
That's true, yeah. And you have to, I think what people realized was that kind of like a parachute, if you want it to come out and have the right shape and not rip or anything or snag or whatever, you have to fold it just the right way. And that's I think why that was kind of one of the issues, and I think why it ripped. And
okay, now let's move on to something that you and I are slightly more aware of, which is the physics part. You obviously knowing a lot more because of active research in the field. So how exactly does putting an infrared telescope out there aid physics, like modern astronomy?
Right. So the first, so there are many applications with the JWST, and I think that's what's really fun about it, is that they were able to make it so that I think for years and years they basically had this open kind of consultation period with astrophysicists and scientists around the world, asking them, what do you want to use this for?
Yeah.
And then I think, well, don't quote me, but I think basically NASA had a committee that decided what was worth or more than, what was worth the time of the telescope. And of course, it's not just one program, but there are actually dozens of little programs, science programs that are being run on with James Webb. That being said, the two ones that stand out the most, I think, and that I know about a little bit, are exoplanet searches and study, and then completely like on a much larger scale, studying like the formation of large scale structures and the earliest structures in our universe by looking very far away, and that's because both of them need that. Both of them can benefit from it from looking at infrared radiation. Obviously, the one for example for the Hubble Telescope is super. It's kind of, when you think of it, it's kind of obvious because essentially what you have this thing called redshift in cosmology, which so I guess at any point, if there's anything I'm going to say that it's a little technical, just let me know.
Before we go
Sure.
into the redshift part, just a quick question. When you say looking into like early structures of the galaxies, how exactly are we looking back in like time for non-physics audience?
How far back?
Or like, no, how do we look back in time, and how far can we look with it?
We can look back. So we can look back in terms of years. We'll be looking back over 10 billion years ago.
Okay.
So we'll be looking at light that has traveled over 10 billion years to get to us. So the universe is about 13.8, I think, billion years old, and we should be starting to see structures after about after a few, after a few 100 million years. So essentially by the time you get to so around 10 billion to 13 billion years ago, you can look at some very late stuff. What becomes a little bit more tricky actually is that at those epochs you end up with a universe that is expanding at a much different rate than it is today, and so cosmologists tend to think about it, think about the universe in terms of this expansion. And so they'll tell you, oh, that's very early in the expansion, or oh, that's very late in the expansion, and with that, and they use this fancy word of saying, oh, that's very large redshift or very low redshift respectively. And the reason is really just because so really they're synonymous, and that's because the light that has been coming from so say you have light that comes from, say, only a billion years ago, that light will have time to travel to us in an expanding universe, and so the light itself, the wavelength of the light itself, will actually be stretched. And so when it arrives to us, it'll be redshifted because of this, meaning that it'll be more, if you had something that looked more blue, it'll look more red by the time it gets to you. Redshifting is just an expression, but really it could be something that goes from X-rays to ultraviolet. That's redshifting technically also, as long as the wavelength is growing basically. And blue shifting is the opposite effect. The opposite thing is it just means you're going in the opposite direction. And the thing is that in the late universe, the universe has been expanding very slowly. But in the early universe, the universe was expanding very fast. And so if you take a million years, you wait a million years for light to get to us 10 billion years ago, that's going to be a lot of redshift. True. But today, if I wait a million years, say I'm looking for something that is like the Oort, and like, I don't know, the Oort, no, what am I saying? The Oort cloud, sorry, in the, sorry, I think the best example would be the, either the galaxy that is the other galaxy that's next to the Milky Way that is going to collide with ours. I forget the name now. Andromeda, thank you. Yeah, I think Andromeda is pretty good. It's just a few million years ago, light years away, sorry. And if that one came, if you get light from that one, then the redshift is much smaller from that distance, right? And so people tend to think about redshift because I guess when you look back in time, you
Mhm.
look into you look into stuff that has been redshifted a lot, and so people call that, redshift 10 or 20 or 100,
Okay.
given how much the universe expands since now. But really, really the reason we look at it, we think about it that way also, is because we know that what the temperature of the universe is today,
Mhm.
meaning what the characteristic kind of energy of like radiation, for example, the CMB is.
Yeah.
And if you look at something that is, say, at redshift 1,000, for example, then you know that that temperature is 1,000 times hotter,
Mhm.
and that energy was 1,000 times hotter, and that could tell you, now we're in an era of the universe where hydrogen could not have formed, for example, and been stable, or further back, stable nuclei could not form, for example,
Right.
for helium or other things like this that have very light densities.
Right.
So that's kind of, anyway. So the point is, so that all this to say that James Webb is going to look at higher redshift
Mhm.
than Hubble could have ever done, meaning it's going to look
Okay.
much further into our past.
So in terms of looking back in the past, so for cosmology, where we're looking at the bigger scale of things, but on a smaller scale, like what kind of local science can we use it for? Because like for the case of the Hubble, you could look at both very far away galaxies, but also like nearby planets and stuff as well. So like you mentioned, exoplanets, etc. So how exactly does that part of the astrophysics work?
Right. So I think the important part is that there are a lot of well, actually, I'm gonna take a step back.
Mhm.
So exoplanets are a fascinating topic, and I should say that it's not the thing that I've specialized on, but
Mhm.
essentially, since we've been starting to see them since maybe the 80s, 90s, I think.
Okay.
And where we at the time would only see a little bit of them, and then Kepler went out and we saw thousands of them, and we realized that there are a lot of exoplanets out there. The
Mhm.
question was to try and find one that, of course, well, so the exoplanets obviously answer a few questions. One of them is, what about star formation? It tells you some things about uh, um, what the clouds of dust and gas were
Mhm.
like before the stars were formed, um, because the heavier elements and that do end up going into the stars will either end up being part of thermonuclear reactions,
Yeah.
or will just fall to the center or whatnot. But so what's nice is to try and to be able to look for these heavier elements in
Mhm.
these planets, to try and get a sense of how much of it was there before,
Right.
and that can tell you in turn a bit about the history of galaxies and how they've evolved, and
Mhm.
notably how much, for example, how many stars have been there
Yeah.
in the past to create those elements, how many
Mhm.
supernova also happened, what the mix of those was. You end up with so there's still, people tend to think that scientists, maybe we know a lot more than we than we really do. The reality is, there's some things that we have a good idea on, but a lot of stuff we still have just models for, and they're competing models, and it may not always look like it, but they do have kind of big consequences. So there's galactic evolution, structure formation evolution a little bit, and that can be on at later times, low redshift, be answered by exoplanets a little bit, but
Mhm.
mainly exoplanets, I think, to be honest, people search for them because they want to find extraterrestrial life
Mhm.
and or a possible planet for us to live in one day,
Right.
which is, I mean, of course, it's a great idea, and we should. It's great to have options, when you're choosing anything, when you're shopping for planets,
Yeah.
or when you want to or if you mess up the planet we're on now and you want to find a new one to live on, and Mars obviously can be terraformed, but that's a whole other topic. Um,
It's a nice
which
T-shirt when you're shopping for planets.
yeah, when you're shopping
Yeah.
for planets, exactly. Um, and I think at the moment we're encouraged by the idea that we almost haven't found a single star that doesn't have exoplanets yet.
Yeah.
Some of them are gas giants like Jupiter's and stuff, on which we would probably never be able to live unless we were orbiting around them, maybe.
Okay.
But I think also one main thing is and particularly on little rocky planets, although that is always harder because there's so I can get into like the different ways of detecting exoplanets,
Mhm.
but the important part about what you want to know in an exoplanet is what is it actually like,
Mhm.
and finding any information about it is always very hard because they're so tiny compared to the star, and we're already looking at a star that looks like a point.
Yeah.
So here you have but there are tracers. There are, and this woman called I believe called Jane Slater from MIT. Uh, she is famous for in the 90s proposing a method of looking for the atmospheric content of exoplanets by looking at absorption lines.
Right.
Because obviously the temperature of the atmosphere of the exoplanet is lower than that of the radiation from the sun.
That's true.
And so it will absorb some of it, just like our planet's atmosphere absorbs some of that radiation. And it absorbs it at specific frequencies.
Right.
For example, we're very lucky that we have like an ozone that absorbs some very harmful UV radiation. And that's the specific bandwidth kind of that we don't want, and it's good. But there's also some obviously some infrared radiation that can be absorbed, notably by carbon-bearing molecules like CO2, for example, which is one of the things that one of the reasons that our atmosphere is heating up, obviously, with global warming. But but more importantly, if you're looking at an exoplanet, you can look for those molecules in that atmosphere by simply saying you have a sun, you have a planet, and that radiation is going to go through that planet's atmosphere before it hits us, before it hits James Webb.
Yeah.
And James Webb sees exactly what we were exactly that. It looks for those kinds of wavelengths that could be absorbed, and so could give you the signatures of a lot of molecules that we haven't been able to look for yet in exoplanets.
Right. Okay. Yeah. So basically, it basically gives you a print of whatever's not being observed, and then you can reverse engineer your way to what is being observed.
Yeah, exactly. It's telling you from what is being absorbed. It's telling you what is in that atmosphere.
Okay.
And what's and the mix of those also, so the relative abundance of them. And I think that can end up telling you, especially if you have like and that can end up giving you signs on what kind of processes life might be using on that planet. For example, on Earth, so Professor Slater was talking about, well, what if you had aliens on those exoplanets and they're looking at Earth? What would they see? They wouldn't see, cities or the Great Wall of China. They would see oxygen absorbing at a very, O2 absorbing at a very, and CO2 absorbing at a very specific wavelength. And in fact, if they measured enough, they'd probably be seeing more and more absorption of CO2 instead, and probably indicating that something is going on this planet, and that there's that'd be a strong sign for life for them.
Right.
Yeah.
Right. So going back a little bit to your area of specialization, you said that you're working in dark matter cosmology. So how exactly does something like this aid your research or research in the field that you're working in general?
Right. So there are a few ideas out there. I think it's difficult to give like a single straight answer of like, oh, this is exactly what it will do, because I think it's more that it will give us it'll give us a whole bunch of information about structure formation in the early universe, is the short answer. The longer answer is it will give you it'll tell you the rate at which galaxies started to form, at which clouds of hydrogen started to clump together, essentially. And that's very important because it'll give you signs as to when you're looking at the data, you can look for any funny things going on, for example, from dark matter, perhaps, whether it's decaying into something that's standard model related and therefore affecting the dynamics, or whether you're looking at some kind of input of energy or radiation, for example, or whether it's or interacting in any different way by absorbing some wavelengths, or even just by not clumping together the dark, because the dark matter itself should be the seed of structure formation in lambda CDM. That's the standard model of cosmology. And it would tell you, therefore, if the structure formation happened at the pace that we predict.
Right.
And that is very important, because it kind of gives you a sense of how the dark matter is behaving with the standard model, but also with itself, and also tells you a little bit about whether or not and then ultimately tells you how the rate of expansion is evolving during that time, and whether or not it's following kind of a vanilla, meaning like a basic lambda CDM scenario, or if we need to add some new ingredients, because the rate at which we believe it was expanding at the time doesn't quite seem to match what is based on, well, and I should say that's the rate that we infer based on data that comes from like the CMB, which came from even before that kind of was released into the universe, even before that structure formation really started. And by inferring that rate of growth, and then inferring the rate of growth even today, we realize that rate of growth, just based on the CMB, that initial radiation, doesn't seem quite to match with what we're just seeing by looking in our backyard, our cosmic backyard, just like the galaxies around us, the stars, that the kind of like standard cataloged stars that we're using to kind of create a sense of how far things are from us and how fast things are moving apart from us. And that's the H0 or Hubble tension, which of course you'll talk about more next month, and I look forward to seeing that discussion. But I think the point is, it'll answer. So I think it'll answer a lot of questions about how dark matter behaves. And it can, I think, constrain a lot of different models of dark matter, because what maybe some people don't always realize is that there's dozens, hundreds, if not more, of models out there of how where dark matter comes from, and therefore how it behaves.
You mentioned like using hydrogen clouds, and another like just one concept that we've repeatedly come across in almost every astrophysics class that I've studied. Studying hydrogen is and hydrogen clouds is like a very important basic that like pretty much every astrophysicist or cosmologist uses in like furthering their research. So how exactly, like why do we need to study that? Like how exactly would the JWST assist in studying and helping us understand like the basics much better?
Well, as in the clumping, I guess, of hydrogen, for example. Well, I think that it'll tell us, it'll be able to tell us how that hydrogen started to form compact objects like stars, so that they could, which then started to radiate out at times where the light that is that those objects were creating was at a wavelength that now, when it is obviously it's a spectrum, but that whole spectrum gets redshifted and is essentially now in the infrared, and so we'll be able to see that in this. So essentially, we'll be able to infer the position of and the density of hydrogen clouds and structure from hydrogen from the amount of stars basically that start to form. If you don't have stars, then there's nothing really there's not much that you can look for in I would say in these wavelengths ish, like of order nanometers, anything. It has to be but there is, and we can get to, there is one other probe that kind of one last trick up our sleeves that is kind of a emerging field in cosmology that I'll get to in a second. But just to finish on hydrogen,
Yeah.
what's great with that is that it will be able to see that light, and it'll also be able to see when that light is lensed, for example, gravitationally, and so it will be able to essentially start to make a map
Right.
of the amount of hydrogen and where it is, and make a large scale structure map of that sort of intermediate times, pretty early time, but intermediate time on universe.
Okay, yeah, makes sense. So before we move on, you were talking about like the
Oh, right,
last
right.
thing in cosmology.
Well, there's this really exciting
Last
thing in
trick.
cosmology that I can't, I guess I can never stop talking about. Is it's 21 centimeter cosmology. I think it's kind of like well, I don't think it's underappreciated, but I think it's people don't necessarily understand it very well. I think even cosmologists, a lot of them don't. And there's some teams of people who have specialized in it, but it's become such a challenge experimentally to get any kind of signal that just because of local astrophysical foregrounds, like noises, that it's just taken much longer than we expected, and everybody's been kind of bored and moved on, basically, because a lot of the theory has been done for it. And so the experimentalists, though, are having a blast still. People like me, though, they're kind of waiting for the results to come out to finally confirm or not what it can constrain. But anyway, the point is that there are big experiments. One that's just started being built last summer, actually, called the Square Kilometer Array, which is literally, as its name says, a kilometer squared of giant, like 20-meter diameter radio dishes in the South African desert that will be picking up. They'll be pointing all in the same direction for hours at a time to try and make and pointing everywhere to try and make a map of the sky, but it will do it at a very specific frequency. So people, this is perhaps something I didn't know even when I was before I was a physicist, is that a radio signal and light is the same thing. It's just a different frequency, and the pickup that frequency, you can, well, when you're looking at something that's like in every case, what you do is you need to find a medium that's going to pick up that radiation, that photon essentially, and is going to create a little electric current from it, right? And then it's going to come into our computer that way, and we can register it. And in this case, the way to do that is, instead of having like the human eye, or having some kind of equivalent to that, which is just like a big like chip that is going to pick up like light, you're going to have now this you're going to have a similar thing where, how in telescopes also you have big mirrors sometimes. We have a big mirror, just like, well, actually, just like with kind of like with James Webb, but also you have this in Hubble and with others, which is a big mirror that maximizes your collecting area, and then it all points it to the same spot.
Right.
Well, really, a satellite dish is the same thing, except it's not except we don't see it as a mirror because it just doesn't reflect light that we can see in the same way. But when it comes to 21 centimeter or radio light, if we could see in that frequency, it would essentially look like a mirror to us, like giant mirrors.
Okay, so just I have a question following up on that, but just to back up for a second, like, what's like the definition of 21 centimeter line? Like, how do you observe something like that?
Right.
What is it?
So the 21 centimeter line is, by definition, the electromagnetic radiation that has a wavelength of 21 centimeters.
Okay.
And that's actually very long. It doesn't sound like a lot, but it's actually it's like tenths of a micrometer for light that you can see. So this is much longer. This is almost, this is tens of centimeters. And then of course, if it's redshifted, then it's meters or more long.
Oh, wow.
So it's actually a very long wavelengths. So this is why you need, by the way, if you have a telescope that's smaller than the wavelength that you're trying to get, you won't even be able to actually probe anything, really, right? Your resolution is going to be terrible. So that's also why you have very, very big, another reason why you have big dishes. Of course, the larger the dish also, the more kind of exposure and surface that you're seeing with, but anyway, but the reason it's special is because it comes from a special transition of hydrogen called a hyperfine transition, which is very it's technical and doesn't matter too much. The point is that it's very low energy, that's why it's very long wavelength, and it doesn't really it kind of does its own thing in the early universe, meaning that it doesn't really have the same sort of temperature. So you can associate kind of with any radiation a temperature, and that temperature doesn't really match that of the CMB, which is the main source of energy for a long time. And that means that you can actually look at it in the sky. You can look for 21 centimeter radiation that'll look different than the CMB. If it wasn't the same, then you would just look in the sky and you'd be like, yeah, that's the CMB. But if it's a different temperature, means more specifically 21 centimeter than the CMB should be at, because the CMB is just defined by temperature, meaning that it gives a whole nice smooth spectrum. If you see a little peak in that spectrum at the 21 centimeter line, you say, aha, there's some hydrogen in there that's not really, interacting with the CMB enough that it can do its own thing, and therefore I can actually look at that and given the amount of 21 centimeter radiation, I can actually infer how much hydrogen is there. And I can do this in any direction, basically. So I can start to make a big map of the sky. And what's really nice is that this is a very, very low energy thing that you don't need to ionize the hydrogen. You don't need very hot hydrogen. You don't need stars. You don't need any of that. You can literally, in just like a big diffuse gas of hydrogen, have this 21 centimeter radiation coming to you. So that means that before any structure formation, you could start to probe the structure of the universe anyway, which is really great. So then you can start pushing to a redshift of 100 or more. So for reference, a redshift of 1100 is when the CMB decoupled from like the primordial plasma of the universe, right? So before that, you don't really know much besides what the CMB can tell you. And then after that, there's this region called the dark ages, where there's no stars, and the CMB is decoupled already. So you don't really know, and the CMB is just, it's just floating in space, and it's starting to slowly clump a little. I mean, it's lensing a little bit, but barely. The point is that there's no other probes, right? And this is maybe the way to light up the dark ages, basically. So that's why it's so exciting, but it's also very difficult, and it probably merits its own podcast.
So moving towards the end of the discussion regarding JWST, like you suggested, like around the time Hubble was made, a few years in, they were already planning the James one.
Right.
Do you think this is it, or do we need something else? Like, where are we headed? What's the future of?
I'm a physicist. I wouldn't be good at my job if I didn't say I want more money. I mean, we always have ideas for new projects, and not just because we want job security. Although I do appreciate James Webb and all the money that's been put into it, because it does give us that. But the point is, there's a lot. There are a lot of projects that have been proposed, and new ones probably that will be proposed in years to come for discovery of amazing new physics. One of the biggest, obviously, so there's 21 centimeter, of course, but that's being built currently. I don't think there are any. I think that it's good that the community is concentrating on the SKA, because it's meant to be the first experiment that will see definitely a 21 centimeter line, I think.
Okay.
I mean, I'm quoting a 21 centimeter expert when I ask him, will you see the 21 centimeter line? He says, well, it'd be very bad if we didn't at this point, because there's expectations and they think they will. But the other major probe, I think so there's two directions. I think I see astronomy going in now. There's gravitational waves, and obviously there's LIGO, and there's more coming up. There's there's Kagra, for example, which is a Japanese LIGO that just came up recently.
Nice. But
there's also their sensitivities aren't very good yet, but they'll catch up. And then there's this idea of like lasers, but in space between satellites now, called LISA, which would probe like a whole different region of gravitational waves, whole different frequency range. Because then again, just like with Hubble Telescope, you have frequencies at which an experiment is sensitive to. And then you can go into the infrared of that, or into the ultraviolet. Well, the same thing with gravitational waves. Now that we have them in just a small frequency, right? The ones that we can see, now we want to start expanding and start looking at the whole region, the whole spectrum of gravitational waves. And hopefully even find like kind of like a cosmic background of gravitational waves, just like the CMB is, but for gravitational waves. But that's another again, a whole other topic for a whole other podcast. It's just, it's really exciting stuff. There's a lot of stuff. And I would be amiss if I didn't mention LUVOIR, which is is at the moment I think infrared, but also UV. I think they're doing infrared, a bit more infrared and a bit of UV now. Telescope that NASA is currently starting to develop now that James Webb is up. And the good news for people developing LUVOIR is that it's the same conceptual design, so it looks very similar, but it's going to be even more massive. I mean, even more massive. Like it's going to need one of those like giant. Actually, no. Even the most massive of Elon Musk's telescopes will not suffice. Rockets will not suffice.
Okay.
He's basically they're in discussion. He's in discussion with NASA at the moment, and they're starting to commission design for an even more like something even more massive that'd be able to put a payload that's even larger, basically.
Oh, if any of the engineers are watching, you've got a task at hand. Design a rocket big enough for it.
Yeah.
Right. So I think from the James Webb part, that's all of it. And thank you so much. That was very informative. Before you go, I have two fun things to ask. One book that you would recommend, science, and then one like book generally that shaped you as a person. And then the second thing being, who's inspired you to be doing what you're doing?
Book in science. It depends. For lay audience, yes.
Yeah. Or just a physics book or anything that shaped you. Like
the book that shaped me as a kid, I think that got me completely addicted to this was Universe in a Nutshell by Stephen Hawking. That one was great because it was advanced for people who are quite nerdy like me, but it was also made simple enough. And I think that was really, I think that sometimes for people who have a genuine interest and who are scientifically curious, and aren't too bad at it, they things like some programs can be a little bit like not specialized, like not advanced enough, I think. So you want something intermediate, and that's kind of intermediate. So that was great.
Right. And one role model in the field who inspired you to be doing what you're doing?
I have several, of course, but probably to date, Lenny Susskind. But he basically, I wasn't in physics. I did a lot of other things before physics, and I didn't think I could. I thought I wasn't good enough. I didn't have the confidence. But so there's Lenny Susskind, and I'm sure thousands of people would say that they have that he's his role model. I've actually heard someone at King say it, but when I heard his story from being able to come from, a slightly disadvantaged background with a family that was not at all scientific, and just really being able to get himself all the way to becoming head of Stanford's physics research, I think is remarkable. And I think what I love about him is that he's not necessarily the most like a technical mathy person, but he's extremely he's extremely intuitive. And I think he highlights the fact that to make great contributions to physics, you don't need to be a mathematical genius. Rather, I think you need to have really great intuition and be not too bad at maths.
That's true. Yeah. Well, thank you so much. On a side note, Leonard Susskind, I think, has a very interesting GR series on YouTube. Should check it out. Yes, do. Love it. Well, this was great fun. Thank you so much. You've taught me in class, but this was a lot more fun and a lot more informative. Yeah. Yeah, thank you. Thanks for inviting me, and anytime. Thank you so much. Yeah.